Hello everyone, this is Srinivas from A Star Express, and in today's video we will be solving a physics paper 6 or an ATP paper from the May June 2024 series variant 1. Question 1. A student investigates the stretching of a spring. Figure 1.1 shows the setup. The student measures and records in table 1.1 the unstretched length L0 of the spring. He does not include the loops at the ends of the spring in the measurement. The value L0 is the length of the spring when the load L on the spring is 0 Newton. Describe one technique you would use to obtain an accurate value of L0. Draw a diagram to illustrate your answer. Okay. So, one of the most important things that you need to remember whenever you have a vertical scale and whenever you need to measure a horizontal frame of reference. So, this is the horizontal frame of reference that we will be measuring since we are not measuring the loops at the end of the spring. So, we're measuring from here to we're measuring from there. Okay. So, whenever you're measuring a hanging horizontal frame of reference, you should always remember you to use a set square. So a set square just acts as a pointer or just acts as an axis that you can measure with. So for example, when I am placing my set square like this, a set square is just a right angled triangle that you can find in maybe your geometry box or just any, it's a very common geometry tool, and you can position it on the meter ruler in such a way that the horizontal part of the set square, it aligns with the horizontal frame of reference of the spring or any horizontal or anything that's hanging, and it aligns with the meter ruler so that it aligns with the scale of the meter ruler. This enables us to know that we're measuring exactly perpendicular and that we're not measuring an angle. This part, sorry, this part of the set square allows us to measure exactly perpendicularly. So what that means is when we align this part of the set square with the meter ruler's boundary, we know for sure that the set square is exactly parallel, exactly horizontal, and we know for sure that we're measuring the right length. And secondarily, the longer part of the longer flat part of the set square, it allows us to actually measure, and it extends to the horizontal frame of reference, allowing us to maintain a straight line rather than judging by eye, which is extremely inaccurate. So for a drawing, you can just draw a set square like this to show that you're measuring to the end of the spring. So to describe this, you could just write use a set square to mark end of spring. Secondarily, another common use case in ATP papers like this in physics generally is the parallax error. So the parallax error is about not viewing something exactly perpendicularly. For example, if there is an object somewhere here, and if you're viewing it like this, or you're viewing it like from a downward angle, or you're viewing it from an upward inclination, the markings on the scale would appear differently to you because of the different frame of reference that you're using. So for example, the center of the object might look positioned here when you're using the upward frame of reference. When using the downward one, it might be positioned here, but when you're looking exactly perpendicularly to the scale, the scale is the markings on here. So when you're looking exactly perpendicularly in, sorry, when you're looking exactly perpendicular to the scale, you know for sure that is the right marking. So this is known as parallax error, and even though the exact word parallax error is not credited in the marking schemes of many ATP papers, the exact word, remember to not write the exact word parallax error. It's just a concept, and when you just write parallax error without actually explaining what it is, you will be discredited marks since it is not mentioned in the marking scheme. So you can also write, this is one of the points, but you can also write, view the scale perpendicularly. So perpendicularly means at right angles to, or at a normal to. So like this, when the scale is moving like this, you're watching it perpendicularly. So that's also very important. Viewing the scale perpendicularly is very important since it avoids parallax error. B. The student suspends a load L is equal to 1 Newton from the spring. He records the new length L of the spring in table 1.1. He calculates the extension E of the spring using the equation E is equal to L minus L naught and records the value of E in table 1.1. The student repeats the procedure using loads equals 2 Newton, 3 Newton, 4 Newton and 5 Newton. The readings and results are recorded in table 1.1. Calculate the extension E of the spring using the equation E is equal to L minus L naught, where L is equal to 5 Newton. Record this value of E in table 1.1. Okay, so you measure L naught when there is no load acting on the spring. It is mentioned in the question here, but it's also just common sense, since when there is no load acting on the spring, there is no extension because the spring is not stretched. So any load, any value that's measured, any length that's measured when a spring is unstretched, when it has no load acting on it, that's L naught. So that would be the unstretched length. So you can just subtract the L naught from the L that we're measuring to measure the extension. So 23.7 minus 2.1 is just 22.6. So that would be the extension. Remember to not write centimeter or the units on in the actual table, since it's already been mentioned at the column. Remember that that would lose your marks actually. And remember to maintain 3 significant figures in an ATP paper most of the times, since the values would also be given in 3 significant figures. When the values are given to you in 3 significant figures, maintain 3 significant figures. Okay. Plot a graph of load in the y-axis against E in the x-axis. Start both axes at the origin. Draw the best fit line. Okay. So let's first draw the load. So load Newton on the y-axis, and that would be just 0, 1, 2, 3, 4 and 5. Remember that your graph always has to cover more than 3/4 of the space that's been provided to you, and this quite obviously is doing that. And draw put an axis for the extension, so that would just be, since it's going up to a value of 22.6, let's just use multiples of 5. So 5, 10, 15, 20, 25. It's going to up to 22.6, and the values are quite close to multiples of 0.5. Okay, so the first value is 0 and 0. That's already been marked in the origin, hence the best fit line. The best fit line must pass through the origin, then it's something to keep in mind. Secondly, it's 3.9 to 1, so at 1 it's 3.9, so this is 2.5, 3.54, so somewhere here. Remember that your points that you're marking on the graph always have to be within zero point 0.5 square accuracy. So that essentially means if this is 10, this is 9.5, and you have a value between 10 and 9.5, you have to mark it between these two and put a circle around it just to make it seem easier to view for the actual examiner. Keep in mind that you have to have half square accuracy, since it's been mentioned in the marking scheme and it's something that it's been followed for all these years. So make sure that you're having at least half square accuracy. Okay, then it's 8.5 for 2, so 2 we have, this is 9, 8.5, 7.58, 8.5, and 15. For 3 we have 12.8, so 3, this is 12.5, 13, so 12.8 would be in the middle. For 4 we have 17.2, this is 17.5, so it would be before that. So it would be in the middle of 17.5 and 17. Then for 5 we have 22.6, so this is 25, this is 22.5, and since it's closer to 22.5, we can just mark it at 22.5, since it's just half square accuracy. So when we get a line like that, just use your scale to mark a best fit line that crosses to the origin. Since both the points on the table start from 0, it must pass through the origin, because when there is a load 0, there is no stretched length. The stretched length is 0, so it must be starting from 0. It must be starting from the origin. So position it accordingly. Make sure that you're averaging out most of the points, or at least try to get equal amount of points in both sides of your line. Something like this would be good. Even though only like 1 point is actually passing through my line, there is an equal spacing of points in both parts of the lines. The line is almost passing through the median of all those points, so that's something that you keep in mind. So this is how you would do this, and remember to label both the axes. So this is E per centimeter, and that's load per Newton. Yeah, that's pretty much it. Determine the gradient G of the graph, show all your working, and indicate on the graph the values you use. Okay. So when you're calculating the gradient, remember that you have to use more than half of the graphs, so that you get a better average of all the points there. So for example, at 10 it's passing through 2.3. You can use dotted lines or straight lines. And at 4.6 it's passing through here, so this is covering more than half of the graph. So G is equal to rise by run, or a change in the y value by the change in x value. So the rise is just from 2.3 to 4.6, so it's just 2.3 again, and this is just a value of 10, so it's 0.23, and that would be your gradient. G is numerically equal to the spring constant K. Record the value of K to a suitable number of significant figures for this experiment. Include the unit. Since we got 0.232 the dot, and technically in ATP we can use we generally use all three significant figures, and also our points that we actually marked were of three significant figures. Since there's one significant figure and there are two zeros after the decimal point, these two are also considered to be significant figures. So there's three significant figures, so you would just write 0.230 since there are three significant figures. And the unit here would just be Newton per centimeter, since Newton is rise and the run is just calculated in centimeters. So rise is in newtons and run in centimeter, so that's just Newton per centimeter. So that's the unit. A student investigates the resistance of a wire. Figure 2.1 shows the circuit used. The student measures the current I in the circuit. She places a sliding contact S at a distance D of equals 50 centimeter from B. She measures the potential difference V50 across length D of the resistant wire. Figure 2.2 shows the ammeter and voltmeter. Record the readings on the ammeter and voltmeter. Include the units. So for the ammeter, this is 0.3, 0.32, 0.34, 0.36. So this is 0.36 ampere. And for the actual voltage, it's just 1, and there are 5 bars. There's like 5 spaces between 1 and 2. So for a unit of 1, there are 5 spaces. So each space constitutes of 0.2, since 1 by 5 is 0.2. So this is 0.2, this is 0.4. So it's 1.4 volt. Remember to write your units, since current is measured in amperes, voltage is measured in volts, and it's all also been written on the actual devices that they've shown, on the scales that they've shown. So it's 0.36 ampere, 1.4 volt. Okay. Calculate the resistance R50 of 50 centimeter of the resistance wire using the equation. Include the unit. So 0.36, the voltage is 1.4. So 1.4 divided by 0.36 is just 3.89 ohm. So you can write 3.89 ohm. Since we're keeping three significant figures at all times, just write 3.89 ohm, since it's more safer for ATP. ATP generally follows significant figures of 3. Two significant figures are not really that widely observed. So just keep using 3 significant figures because that's safer. Calculate R1, a value for the resistance per centimeter of the resistance wire using the equation where D is equal to 50 centimeter. Include the unit. So R50 is 3.89 divided by 50, and that's just 0.078 ohm. Remember, including the unit is for the 2 marks, you would be getting 1 mark for the unit and 1 mark for the actual value that you're getting. Since it is resistance divided by the actual distance, it's ohm per centimeter. So it's 0.078 ohm per centimeter. Okay, the student repeats the procedure in A using D is equal to 75.070 centimeter and calculates R2 using the equation R2 equals R75 divided by D. V75 equals 2.2, R75 equals 6.1, R2 is equal to 0.081. The student suggests that the resistance per centimeter of the resistance wire is constant. State whether your results support this suggestion and justify your statement by reference to the results. Okay. One thing to keep in mind here is that any value to be assumed equal in circumstances such as experimental or practical circumstances, the general hallmark is to be within 10% of each other. So if R1 and R2 are considered to be equal, R1 needs to be 10% 10% plus or minus of 0.081. So 0.081 into 10%, which is like the 10% of R2. When you subtract 0.081 plus or minus that 10%, you should still get somewhere near R1. So R1 should be within 10% of 0.081. It should be within that range. It should be either greater than 10% less or less than 10% more. So this is because when you're doing an experiment, a lot of mistakes can happen, a lot of errors can happen, either that be systematic errors in the actual experimental procedure that you're using and the actual apparatus that you're using, or it can be random errors caused by inaccuracies in the students practical, the ways that she's doing the practicals. So the statement that we are going to use here is yes, it justifies this statement, and it supports this suggestion. So because 0.078 ohm per centimeter is within 0.081 10% greater or less, so we can write yes, it supports the suggestion. Remember, this is a very common question, and remember to write exactly like this. Yes, it's supposed to suggestion, because that's what's given in the question, and you can just reciprocate that. Okay, justification. So how you would justify this is this plus or minus 10%. It is known as the limits of experimental inaccuracy. So the limits of experimental inaccuracy. So that plus or minus 10% means this R1 to be considered equal to R2, this R1 should be within R2's limits of experimental inaccuracy. So if that is true, then both of them can be considered equal. So how you would do this is, first you state your values, you quote your values. So R1 equals 0.078 ohm per centimeter and R2 equals 0.081 ohm per centimeter. Both values are considered equal to each other, equal since values are very close to each other. And within limits of experimental inaccuracy. Okay, both values can be considered equal since both the values are very close to each other. Close to each other as in they're like not that far away. 0.078 and 0.081 both are very small values and they're very close to each other, so they can be considered equal. And when you write within limits of experimental inaccuracy, means that we're suggesting them to be equal since they're within plus or minus 10% of each other. The student plans to plot a graph of resistance R against length D to test the suggestion. Suggest suitable additional values of length D to use. Okay, so this can be any value from 0 to 100 centimeter, since we would be measuring using a meter ruler here, mostly using a meter ruler, and when we cross 100 centimeter it becomes hard to measure it, since we either need to use a measuring tape, which is less accurate, or we need to stack two meter rules, which means the spacing, the padding that's given in the meter rule would act as an inaccuracy. So anything between 0 and 100 centimeter, that should be the general hallmark that we're going for. So for example, any value of 30 centimeter, 45 centimeter, and maybe 80 centimeter, these values should be a general hallmark for the values that we can use. A variable resistor is a circuit component that can be made using a coil of resistance wire. Draw the electrical symbol for a variable resistor. Okay, so variable resistor looks like this. It's just a resistor symbol with an arrow passing through diagonally. A student investigates the image produced by a lens. Figure 3.1 shows the setup. Illuminated object XY. Okay. Figure 3.1 shows the height h0 of the illuminated object. On figure 3.2, measure h0. Since I cannot do that here, I will just be quoting the values as per the marking scheme. But remember that when you're measuring with a general ruler or a general scale that you're carrying with you to the exam, remember that you should not quote in three significant figures, since the minimum value that the ruler can be used for is 1 millimeter, sorry, is 1 millimeter. So when you're quoting it, for example, in 15.5 millimeter or 14.5 millimeter, that's bringing unnecessary inaccuracy into it, because you won't be sure if it's either 15.7 or 15.8 or maybe 15.4, 15.3. All that would appear same, because it is a form of estimation that you're bringing into the actual question. So when you're quoting it, even if it comes as, for example, 15.8 millimeter or 15.9 millimeter, just write it as 16. You have to take the lower bound or the upper bound, since only then it's right. So for example, this would be 16 millimeter. Figure 3.1 is drawn to scale. The actual distance u between the illuminated object and the lens is 20 centimeter. Okay. On figure 3.1, measure the distance x, and that would be 2 centimeter. Calculate the scale ratio using the equation r is equal to u by x. So r is equal to 20 by 2, which is 10. So 10 times r is just a ratio between two values, since we have the word ratio is given. So when a ratio is given, remember that you do not need to write the units. Ratios do not have units. The student moves the screen until a focused image is formed on the screen. Figure 3.1 measures the distance y. Y is equal to, it's equal to 62 millimeter, and calculate the actual distance v between the lens and the screen using the equation v is equal to ry, and that would be 62 centimeter or 620 millimeter, since it's into 10. So 62 into 10 is just 620 millimeter. Calculate the focal length f of the lens using the equation, giving your answer to a suitable number of significant figures for this type of experiment. So that would be 15.1 centimeter. Once you finish the calculation, it's just using the values that we've gotten already. So u, we got it for 20 centimeters. So 20 into 200 into 620, because we're using millimeters here, to 200 plus 620, you would get it as 151 millimeter. Since they're asking it in centimeters here, we're quoting it as centimeters. Here you can use three significant figures, because the value that you're getting is in three significant figures, and ATP papers generally like three significant figures, so just quote it that way. And in this type of experiment, it can be difficult to judge the screen position that produces the clearest image. Suggest two precautions or techniques to overcome this difficulty. Okay, as per the diagram, one thing that is missing here is, one thing that is not quoted here is darkness. And another thing that is very important in this type of question is that it is difficult to judge the screen position that produces the clearest image. It's not a general precaution or a general technique that they're asking to reduce the inaccuracy. In this type of experiment, there will be multiple different precautions that can be taken, such as using a center marked lens holder to like judge the actual correct length and everything. But here they've given you an exact condition or an exact scenario to consider, that is too difficult to judge the screen position and the clearest image. So you won't be able to see a clear image when you have a very bright room around you. So it is important that you use a dark room. Maybe instead of a dark room, you could also use a bright actual object. So the actual object that you're focusing, it could be more bright, maybe more powerful light instead of a candle. And another thing that you generally is very important in such questions is that you move back and forth very slowly. So in this type of question, the screen has to be moved. When it is moved, you would be able to judge where the object is being produced and everything. However, when you move the screen very erratically, or when you move it only in one direction, you would not be able to get where the illuminated object, the actual image, is forming. It is important that you move it both ways, and you move it very slowly and very delicately to ensure that the image is formed as sharp as possible. So what you write here is move back and forth slowly. This is a very common question in this type of ATP scenario. They would ask you for precautions and techniques to overcome difficulties. In other scenarios, precautions such as center marked lens holder and view perpendicularly and use a sharpened pencil. These are other common precautions that you generally use in such anything that has imaging in it, such as like using a lens or using a rectangular glass block. That's another very common question in ATP papers. These all these five things are very common precautions, and I urge you to like really memorize these ones, because they would be very important for the exam. And please like memorize these five precautions, but remember to use them according to the scenario. In this scenario, it's only about getting the clearest image, so you can only use the dark room, and you can only use the moving the screen back and forth thing. You're not using a pencil anywhere, so you don't need a sharpened pencil. Your lens holder, the actual distance the actual measuring of distance is not considered here in this scenario that they've given us. So center marked lens holder and view perpendicularly won't be applicable here, but they are very common questions, and I highly urge you to remember them. Figure 3.2 shows the shape of the illuminated object. The image of the object is enlarged. Draw a diagram to show the image that you would see on the screen. Okay, so this is H0 and this is the actual object. Whenever you get a real image is any image that can be derived on a screen. It can be caught on a screen. Whenever you get such an image, it would be inverted, laterally inverted or upside down. So remember to draw the image upside down. So triangle, upside down triangle, and much bigger than what is shown on the object. So like a pretty big upside down triangle. Okay. Okay, for the final question in the ATP paper, this is a very important question, and it's one of the a little bit harder questions to score the whole 7 marks in, but it's very easy to score once you understand what's actually going on. Okay. A student investigates the bending of composite strips of wood when they are loaded at one end. The composite strips are made from identical layers of wood stuck together as shown in figure 4.1. Plan an experiment to investigate how much composite strips bend when they are loaded at one end. Figure 4.2 shows the setup the student uses. The student has a number of composite strips made with two or more layers of wood. In your plan, state the variable that you're testing, list any additional apparatus that you would use. Explain briefly how to do the investigation, state the key variables to keep constant, draw a table or tables with column headings to show how to display your readings, explain how to use your readings to reach a conclusion. Okay, first of all, whenever you see a plan and investigation question, remember to clearly observe the setup that they've given you, or the setup that they've asked to create. So here that they've given a bench, they've given a composite strip that is hanging away from the bench. It is extending from the actual clamp that they've given. So technically you would just be hanging a load here, and this would cause the bench, the composite strip to bend downwards. Since anything, if you have, because it's like a slightly elastic and slightly flexible piece of material. Okay, first of all, they've asked us to state the variable that you're testing. So any variable that you're testing for, that's called it's called the variable that you're testing for, sorry. So you can just write, we would be measuring the amount of bending, and that would just be the independent variable. So the independent variable, or the variable that you're actually measuring for, is called the amount of bending. So that's what you're measuring for, and it's important that you state that separately, since that's what they've given in the criteria. List any additional apparatus that you would use. The main thing that we would be doing in such a question is measuring stuff, measuring the length of measuring how much it is bending, and to do that we would generally use a meter rule. So a meter rule is the only real thing that we need, because we are not measuring anything else. We're not measuring the angle of anything. We're just measuring how much it is bending, and that can just be done by positioning the meter rule this way, measuring the initial length, measuring the initial marking, and once it has bent something like this, measuring the final marking, and that would give us how much it is bent. Okay, then first, for the method procedure, remember to actually title and structure your plan the investigations like this, even though it is not explicitly mentioned in the actual guidelines or the marking scheme or anything. It is better to procedurally structure something like this, because it helps you to focus, and it also helps to mark your paper easily, and helps to focus your response. Since whenever you're being marked for your plan the investigation, it is important that you have a focused response. You do not talk about irrelevant stuff, about like simple details. You would just need to be focused, and you need to mention whatever that's needed to be mentioned. And to a person who's doing this experiment as a newbie, or as someone who's never done this experiment before, just the important stuff. First, we would add a load. Add a load to the strip and measure the amount of bending. That is the variable that we're measuring for. Secondly, we are then, since we would be repeating this experiment for different loads, since that's what we're testing for, how much it's bending when it is loaded differently, when they're loaded at one end. So we would just repeat for different loads and measure amount of bending. Another thing to always write in a plan and investigation is to repeat for the same load multiple times. Only if you repeat for the same load multiple times, with, for example, you're adding the load once again to the strip and then you're measuring it, only then you can actually get an average and reduce the inaccuracy in your question. So repeat for same load, for each load 3 times. 3 times is the general hallmark that you go for, since if 2 values are anomaly, another value is still remaining, and at least 3 points are required for you to draw an actual best fit line. So repeat for each load 3 times and take an average. That is something that you have to repeat in all the plan the investigation, something that you should never forget. After that, something that you have to keep constant here. So the constant variables. So the constant variables would just be, for example, if we would use, since we're just using different loads here, if, for example, we're using a different length each time, the bending would obviously change, because the amount of bending would change with the amount of overhang from the clamp there is. The overhang is just the extra part of the strip that is hanging from the actual bench. So keep the length of the strip constant. Another thing to remember here is that this strip is actually made with multiple layers of wood, and there is adhesive between the actual wood layers. So for example, for a load of 100 grams you're using 2 layers of wood, or for a load of 200 grams you're using 3 layers of wood. That would make your actual experiment invalid, since the amount of wood, since wood is the actual material that's flexing here, the amount of wood would obviously change the flex or the actual bending of the strip. So that's another thing that you need to keep constant, is the amount of wood layers. Another thing to keep constant here is that where you're actually hanging the load. For example, if you're hanging the load here, that would differ from hanging the load here, since there is some extra moment that is acting because the perpendicular distance is greater, but you don't really need to know that for this question. But still, since the perpendicular distance is greater from the actual bench, the moment acting on this part of the load caused by this load is greater than, for example, if this is load A, this is load B, A would exert a greater force than B, it would exert a greater moment. Moment is the rotational force or torque that's created on a pivot angle. So here there would be a greater moment applied because of the actual extra perpendicular distance from the pivot, even if the load is of different weights. So that's another thing to keep in mind. So position of load on the strip. Okay, now the table. So for the plan the experiment, you do not need to actually give the table values, since you do not know how the experiment is going to go. You have not carried out the experiment, so you do not need to give the table values. Actually, if you do give the table with values, it is actually going to reduce marks for you, because you do not know how the experiment is going to turn out, and you should not make assumptions without actually carrying out an experiment. So just the columns. So the first column would be the independent variable or the load. So the load here would be just the load please use a scale and a pencil when you're drawing the table. Since I'm working on an iPad, I cannot do that, but remember to do that while you're in the exam. Okay, so the load, and that in newtons, since the weight of the load is actually what's acting, not the mass. So load in newtons, and the amount of bending, so and that is calculated in meters, since we're using a meter rule to calculate from which angle it's going down. So that would be in meters. So those are the only two things that you need to actually calculate. Another thing, and finally, to conclude, there is always a common conclusion that you use for plan and investigation, and you do that by first asking them compare the values of bending to the load for determining correlation. So this would allow you to compare the values of the load and the amount of bending to find if there is some correlation between them. This is one point, and another point, I would suggest you to actually write both the points, since in some marking schemes one would be there, in another marking schemes another one would be there. From the past papers that I've done, the May 2024 paper is has both of them in the marking scheme, but some papers don't. For example, 2021 or 2020 papers, or even 2016 papers, they have the compare, they might have compare, but they might not have the graph value, or they might not have graphing, and they might have graphing and they might not actually compare. So you should also write about plot a graph of bending in y-axis, since that is the dependent variable, and load on x-axis. And this is actually a mistake from my side. The amount of bending would be the dependent variable, so this is the dependent variable, since that's what we're measuring. Okay, plot a graph of bending in y-axis and load on x-axis, and draw best fit line. This would allow to find the correlation, and that's how you answer a plan the investigation. remember to always write everything that they have mentioned in the question. Remember to write about the control variables, think in every possible aspect, and go through the question once or twice at least to know that to know all the nuances they mentioned in the question. And another thing to remember is that always write repeat for each load, since that would allow us to get an average and reduce the inaccuracy. And please remember the conclusion. Remember to write both the points so that we have a better chance of scoring. And for the other question, remember to remember these precautions very well and to use them as per the scenario. If the scenario is changing, use different precautions, but remember all these 5 precautions, since that would help you for most of the exams. And I believe your exam is on Tuesday, so I wish you good luck and all the best for that exam. I'm sure you do well. If you like this video, please consider subscribing to A Star Express, and see you next time. Bye.